Good morning, everyone. So we'll get started. It's my pleasure today to welcome Professor Rao Kambhampadi from Arizona State University. Professor Rao has been doing a ton of influential work in AI and planning decision services. He is a fellow of the AAAI, AAAS, ACM, was the president of AAAI, founding member of the Partnership on AI, and won several teaching and research awards. If you don't follow him on Twitter, you should. Very insightful takes, sometimes very hot takes, very interesting discussions. So if you don't follow him on Twitter, you should definitely, or on X, you should definitely should. Welcome, Professor Rao.
Thank you. Thank you, guys. And as I said, for the people here, I'm sorry I pulled you in from the beautiful weather outside. For the people on Teams, thanks for showing up. So anyway, I wanted to talk, I guess you can hear me well. I want to talk about some of the work on LLMs and planning and reasoning. In fact, I would actually, while the title says, how do LLMs reason? Actually, I will talk more about planning, which is a very specific form of reasoning. And length generalization actually becomes an important thing in planning. So I'll talk about how do LLMs plan. And then, so as Ahmad said, I'm a planning guy originally, and I've done a bunch of work in automated planning. And then for about 10 years before the last 3 years, I was actually very interested in explainable human-AI interaction, which I know is a bunch of people in MSR are very interested in. So there's actually things about explainability, advisability, and generating common representations between human agents and AI agents. And so we actually have a monograph on our work that is available freely on archive. That you're interested. If you're interested, you can take a look at that. And if you have questions on that separately, please get in touch with me. I'm still very interested in that area, but obviously today we're talking more about LLMs and reasoning. Obviously everybody is suddenly stopped doing whatever they were doing and started caring about what's going on with the LLMs. So I think the LLMs basically have this, as Andres Karpathy says, jagged intelligence. They can do pretty amazing things in certain places and then fail pretty miserably in small variations of that. You can do frontier math, reasonably well sometimes, and then you can also fail on multiplication. So they're just really amazing, and we need to there's a lot that we still need to understand in addition to actually leveraging them. There is obviously, the research, the labs, and the industry in particular has been seriously looking at leveraging it, exploitation phase, more or less. And then we are sort of trying to also, sitting in universities, in particular my group has been trying to understand actually what makes them the credit when the credit is due versus whether actually the credit is partly because of anthropomorphization. So anthropomorphization is actually a big issue that has been a problem in AI for a long time. I think some of you probably might recognize this guy, Rube Goldberg, who wrote Artificial Intelligence Meets Natural Stupidity in 1970 something, like 75 or something. And this was at that time when AI was like a big deal. And he was basically saying, we should try to make sure that we don't anthropomorphize the AI systems and then actually check in an objective way whether they have capabilities or not. And so that's something that we've been looking at. And so while some of this talk actually does talk about the limitations of LLMs, I want you to sort of get a sense that I think it's an amazing technology. It's just great that we have these general purpose external system ones that we never had before. I'll tell you more about that in a minute. But at the same time, there's also significant misperceptions, mislabeling of what their capabilities are, and that actually kind of muddies the waters. So I tend to think that it's sort of like the situation with alchemy. The chemistry is an amazing subject. Chemistry is extremely important. Alchemy is questionable. And then you want to differentiate alchemy from chemistry, and that's basically what we want to figure out for LLMs. And it's great to actually give this talk in MSR where you guys apparently saw the first sparks of AGI. I'm probably in one of these rooms, and so I'd like to try and see my perspective on that. So anyway, the planning part is the one that I was most interested in. Basically, when LLM started when hit the scene, I mean, obviously, pretty much everybody was extremely impressed. I, coming from India, was like taken aback that the damn thing can't make any grammatical error, whereas I can easily generate stuff which is full of grammatical errors. And so the ability to actually do this prompt completion in coherent prose was obviously something that was very impressive. And there's a bunch of things that were great. There's a GPT-3 timeframe. But then the thing that started catching my attention is there's a bunch of papers that started coming up saying, not only can they do this completion, auto-completion of the prompts, they actually have all these other, they have zero-shot planning abilities, zero-shot learning abilities. In fact, for a while there, the most popular title, maybe it's reduced now, for an Achilles or a Rubes paper is LLMs are zero-shot XXX, where XXX is your favorite task on which you called LLM a couple of times and found that it seems to be giving reasonable results. So that sort of didn't make too much sense to me because if you look at it from a system one, system two sort of metaphor, I saw LLMs, again, the original, the conventional LLMs, the one from GPT-3, GPT-4, etc., as essentially this more similar to sort of a system one with humongous external knowledge, digital footprints of humanity that has basically been pulled in, and there is no real reason to believe that deliberate reasoning is actually happening in that. And so I was curious. My prior was that maybe they actually don't have the planning abilities, and yet people are writing these papers. So I was more interested in seeing what's going on. So in fact, it's interesting that given all these papers about LLMs can do planning, etc., back in GPT-2 timeframe itself, why actually do you need the new kinds of LLMs that we started calling large reasoning models, which now are doing planning? Clearly, at some point of time, we were misrepresenting what their abilities are. And it's not very clear whether we are still continuing that misrepresentation. That's something that we want to understand. One thing that I find very useful when I think about LLMs, and obviously the people here for them probably it's very obvious that basically there is this issue of style versus content and form versus factuality. LLMs are basically generative AI systems, and generative AI in general learns the distribution, and any properties of the distribution are some things that it gets very nicely. Style is a distributional property. Correctness and factuality is an instance level property. Just because it's the right style doesn't necessarily mean that this particular instance is actually correct. But then when we don't know the answer ourselves, we kind of glom onto the syntax and the style of it and say it sounds good. And when you do know the answer, then that's not actually a good use case for LLMs. If you know the answer, why are you asking the LLMs? I understand evaluations, we would do this, but end users probably would be using them for problems for which they don't really know the answer. And if it just sounds confident and if it's in the right form, with the right number of aha moments, etc., thrown in, you will start believing it, and that's probably an issue. Civilizationally, we always thought style is harder than content. I keep saying that anybody could have written Shakespearean stories. It was the iambic pentameter that was so damn hard. But now, obviously, it's completely changed. Anybody can do iambic pentameter of nonsensical ideas, and that's become very easy. And so that's a pretty impressive thing that we could do this. So essentially, I think that that's an important distinction to keep in mind when we talk about what happens in terms of their actual limitations. The other thing that sort of is useful, that I find useful, is LLMs have this, basically, obviously, they're doing some kind of an approximate retrieval. It's not an exact retrieval. That is a conventional ones on this humongous amount of data, the digital footprints of humanity that they've been trained on. And that ability, we never had systems like this. We really never had systems. And this thing can only happen at the way it happened, because we had to first put everything we knew onto the web, and then LLMs can come and actually use that. As I say that, if Satya gave all the money to Sam, and Sam was ready with all the GPU power, and they just needed web, and he said, hey guys, why don't you write everything you know onto the web? We wouldn't have had LLMs, because nobody writes that stuff. We wrote it for ourselves. But the fact that they're available, one of the things that makes a difference here is that in terms of our intuitions go haywire in this. So computational complexity of the underlying task has no real bearing. Again, for the beginning part of the talk, LLMs, I mean large language models of the GPT-4 type, and then I will talk about LRMs, which are basically the ones with post-training and test time scaling in a minute. So, in terms of computational complexity, LLMs actually don't care about the computational complexity of the prompt. Whether the prompt is a semi-decidable problem or a constant time problem, they will start typing tokens right afterwards. And so that basically also means is the usual problem characteristics, stochasticity, partial observability, etc., which make planning and decision making hard, don't matter in terms of the LLM's abilities to guess, and then the percentage of wrong answers, as judged post facto, would probably be just as bad for easier versions and the harder versions, computationally harder versions. I'm sorry. And then the other thing is that the background knowledge is much easier for LLMs approximately, and it's something that we don't realize. I mean, so in humans, I tend to think that we are equally impressed by two very different abilities in humans. A doctor who can combine very different, supposedly desperate symptoms and say, hey, this might be the disease you're actually suffering from. And to actually combine that, they need to have humongous amount of knowledge. I mean, and medicine is actually one of those cases where you just need large amount of knowledge, and the reasoning, the inference part is like a smaller part, that the amount of ability to bring large parts of knowledge together. We're equally impressed by that. And Andrew, while sitting in his attic and chugging away for 17 years to prove Fermat's last theorem. And it's reasonable. You should be equally impressed, because none of us have the, the full-on world knowledge, and none of us have the discipline to go do deep reasoning. But for LLMs, the first comes more or less easy. The second one is actually the interesting part, because the first one, basically, that's not the way we learned about the world. And, we just happen to have the entire digital footprints of the humanity. And keeping that in mind, background knowledge is actually very easy for them, approximately. And so they are pretty good at common sense, domain knowledge, theory of mind, analogies. And this is what makes them very good fertile ground for writing LLMs or zero-shot XXX, because you can actually say, look, they seem to be doing analogies. Look, they seem to be doing Salian problem. Look, they seem to be doing whatever you want to think about in terms of this task. So keep that in mind. And then now I get to the state of the art in LLMs that you already know, which is that basically many of you know already, which is you have the standard LLMs, the GPTX, and the Gemini, Llama, and the various models of that type. They basically auto-regressively trained on web corpora, fine-tuned to make them more palatable to the end user, and at inference time are just completing the prompt. Okay, there's this new set of things that start coming up, starting O1 last September, I guess. O1, R1, and they've been called various names, long chain of thought models. We basically coined the term large reasoning models in our group when we were trying to evaluate O1. Now it seems like it's become partly other people are using it. So, it's a reasoning model or large reasoning model. So standard LLMs based plus test time scaling. Test time scaling essentially can be thought of as using the LLM as a generator, better than a random generator, significantly better than random generator, and then having something in the loop that actually checks the generated suggestions are reasonable or not. And so that is a generate test with verifier in the loop. And then, in fact, we have done some work on LLM-Modulo architectures that I'll talk to you about. That basically is having, for cases where they may actually be formal verifiers, generate test with verifiers would actually be very possibly good idea if you have a good generator. And LLMs are much better generators than random generators. And then there is a post-training with synthetic data backed by verifiers. That we'll talk more about, but again, it's an interesting talk to give here because a bunch of you are actually working on this stuff, and so you pretty much can complete some of the things that I'm saying. So the supervised fine-tuning and RL on not just the solution, the problem and the solution, but the problem intermediate tokens and the solution, and you're essentially training on that. And in some sense, actually, that's sort of not the fact web. If you think of the original web as the fact web, you had to generate the reasoning web, because for a reasoning web, you essentially have to generate examples of this for different lengths of the problems, for example. And so this is what is going on with the synthetic data. It's a way of thinking about what's going on with the synthetic data. The synthetic data is being used with one generator to actually increase accuracy by the next time and so on, the next epoch, etc. So the foreshadowed summary of this talk, I don't know how much I would actually get through, but the foreshadowed summary is that LLMs just trained on the web corpora are known to have severe limitations on planning reasoning tasks. My group has done a bunch of work, other people have done too, but I'll show you some of those results. But then they could, however, be used as generators in a generate test cycle to give a robust reasoning performance. This is a form of test time scaling. Essentially, you're using it as a generator, and then you're checking outside. And then if the better the generator, the faster you can actually get to the solution. The improved reasoning abilities can be compiled into the base generator LLM, either with SFT or RL. This is the new thing that we started doing. But then that is essentially what we are doing is, we are, for a fact web, you just have to compile it once, but for reasoning web, you have to do it many, many times, because as the length increases, you still need to have the problems corresponding to that length of the problem instances. This wouldn't have been required if LLMs are actually just able to learn and execute procedures, but I'll show you results that basically that they don't seem to do that. So the resulting larger reasoning models have no correctness guarantees, neither do LLMs, but nor do LRMs. They don't have any correctness guarantees, but there are better generators. And then the anthropomorphization, and so for the LRMs, as I said, there's a test time scaling as well as a post-training are the two things that, obviously are things that basically people are looking at, and we'll talk about some of the misperceptions about them. But I think the anthropomorphization, which is an issue with LLMs, is continuing to be an issue with the LRMs. And that's an interesting point that I'll hopefully get. This also is a foreshadowed one that I'll get back to towards the end of the talk, that I want you to kind of think of the fact that LLMs can be, large reasoning models can be understood as incrementally compiling verifier signal into the underlying generator. This is a guess. I mean, I don't have complete proofs on this, but if that is the case, then that approach can suffer from the similar amortization issues as normal fine-tuning. The question essentially is, the work that you did memoizing, fine-tuning all this data, is it basically being paid for in the inference time? And that's something that we ignored in general in LLMs, because somebody else is paying for the training and we're just using it in at the inference time. But from a CS point of view, computer science point of view, that does make an important issue. The other point is that there seems to be considerable misperceptions about the role of the intermediate tokens. They've been called chains of thought, they've been called reasoning traces, and all we really know is intermediate tokens help the LLMs. But somehow we started saying they also help the people reading the LLM's mutterings. And there's this whole interesting issue about looking at these mutterings that sometimes go on 30, 40 pages for even small size problems, and trying to say, wow, that's what it's thinking, etc. And so again, anthropomorphization has always been a problem in AI, and LLMs just make it so much easier, so much easier. And the question, of course, is it doesn't, just because you say it sounds like humans doesn't necessarily give you any actual theoretical understanding of it. So it's worth understanding, in fact, whether intermediate tokens are really supposed to have any semantics. I'll tell you some work that we have done more recently showing that in certain cases, you can actually evaluate the intermediate tokens and show that the correctness of the reasoning traces is disconnected to the correctness of the solution. And that, in fact, you can even train with the wrong reasoning traces, and you can get to the same level of accuracy. What that basically means is these mutterings are helping LLM somehow. We still need to figure that out. Clearly, it is helping because of the the evaluations we are doing, but they're not necessarily not necessarily telling us something about what's actually going on. And because people assume that this is actually telling us something about what's going on, then you have all these other papers like Anthropic last week saying, oh, it turns out LRMs are not faithful to their own mutterings. I would actually start by sort of saying that I never expected them to be faithful. And so why did you have to show it? You only have to show it because other people thought they are. Okay. So again, I think one of the things that we do know is this thing that I'll get back to, that if you're giving a task prompt to an LLM with LLM and then it's giving a completion and you're trying to check if that completion is the correct answer, that probability is lesser than task prompt plus there exists some intermediate tokens that if you give to along with the task prompt, LLM is generating a solution that's more likely to be correct. And this is a reasonably good empirical understanding we have as to what these intermediate tokens are. People are actually putting all sorts of interesting overloading interesting semantics on top of that. So, and then finally, one of the other things is the role of RL versus iterative SFT needs to be understood better in the LRMs. There's a whole bunch of, I keep thinking that there's always a cheering squad for RL in AI because it's one of these great ideas and we really wanted it to work. And once in a while, it seems to kind of maybe working. And the question is whether or not it was actually the RL or something else could have been done. We had gone through this in RLHF, for example, and now we are possibly going to doing this in the course of RL in DeepSeek sort of approaches. Again, some of these really are dependent on the analysis of DeepSeek style models, which actually bothered to write a paper. OpenAI, we have no idea what they're doing. I guess some of you guys know what they're doing. I have no idea, but certainly sitting where I am, I have no idea what they're doing. So again, I think there's a bunch of papers you've written on this. If you, after this talk, want to just give like a quick overview, then I would say these sorry.
I have a question. I raised my hand for a long time, so let me ask
I'm sorry, I don't get to see the.
So if in the previous slide you said, I don't know whether you're gonna expand it, but in the previous slide you said, I think you're moving forward, not backwards.
Yeah, sorry, yeah.
Yeah. LRMs can be understood as incrementally compiling verified signal. What exactly you mean by that?
Yeah, I'll get to that. I'll actually show a full signal. So I was basically, since you asked, so the way I would say is think of the R1 in the following way. V3 model already has ability to be giving correct solutions at pass at 5 or pass at 15 for some subset of solutions. And then what you are doing in the training phase, in the LRM training phase for the V3, basically is you're taking this pass at 15 over the problems and getting it to pass at 1, close to pass at 1 for some subset of some length of the problems. And once you do that, you now have a better generator for larger reasoning problems, and then you can then bootstrap it next time around. So in fact, when DeepSeek writes distillation, and then the distillation seems to work just as well, part of that really is that the model after which became good at pass at 1, essentially is actually a better generator for the longer length solutions already. I'll get into it more, but that's basically the intuition on that. And as I said, these two papers might be of interest to get a quick overview of some of the things that I'm saying. So coming back to LLMs, so there's the planning stuff. As I said, I'm coming from planning, and so first thing I did was, in automated planning community, we have these competitions for planners, and they have some domains that we use regularly, blocks, world, logistics, and so on. So we basically threw that onto LLMs, GPT-3 in the fall of 2022, which looks like an ancient history, because already people are saying they can do planning, and it turns out they couldn't, and they're actually pretty bad in terms of the percentages, in terms of the planning accuracies. So actually, this was the time already when I believe one of the students, Karthik Valmikam, who is the first author, he went to NeurIPS 2022 in the LLMs for the foundation models for decision making, and there's an entire huge room full of people who are saying LLMs can slice, dice, everything. And there's this one guy saying, no, they can't do the planning part. And so it was kind of a fun part for him. But anyway, this paper actually, came up and like 2 years back, 3 years back. And then we did extensions of that in a more careful systematic studies. There's like a NeurIPS spotlight on the analysis of these sorts of planning problems. And we also generated a plan bench, which with respect to these kinds of planning problems, which involves both plan generation, cost optimal planning, verification, reasoning about execution, and so on and so forth. And that plan bench is available on GitHub. And the general quick overview of summary of that whole direction basically is LLMs can't do planning in autonomous modes, and LLMs like GPT-3, GPT-4 sorts of things, and they really didn't, and that didn't really change as long as we looked at conventional LLMs. This is like a 2024 version where Karthik keeps actually redoing these experiments whenever new LLMs come. And so it basically, you see that you're only showing two domains here. There's blocks world, and it slowly seems to be improving, but it's still not 100%. This is like supposed to be the cheapest kind of a problem. And then there is this thing called mystery blocks world that seems to be stubbornly stuck at below 5%. And what's this mystery blocks world? One of the things about trying to decide whether something is doing reasoning or not when the answer is correct is actually, you can't tell. It could actually have retrieved the answer. You heard about it. In fact, I have this story. I don't know how true it is. There's an apocryphal story that in the beginning, Microsoft invented this interviewing procedure where they'll ask reasoning questions to people. And one of those questions was, why are manhole covers round? And the very first guy who had to answer this with somebody looking at him or her had to figure out, why is that required. But now onwards, if you ever ask this question, all you know is they have looked at the same question banks that everybody else has looked at. But they're smart, so they'll think as if, they look as if they're thinking for a while rather than right away blurt the answer and say, I think this is the reason, and you are sufficiently impressed. I'm not saying that that's happening, but that's like one of the issues that you have to worry about with reasoning versus retrieval. And so one thing that we actually did was actually mystery. This was something that was done in planning community. People were worried. Drew McDermott back in 1998 was worried that maybe people are writing domain-specific planners that can be highly optimized for specific domains, and whereas we are interested in domain-independent general solutions. And so what he did was try to change the names of the domain objects. Instead of putting up a block, you would say attack an object. Unstacking a block, you'll say feast object from another object. In general, global replace one word with a different word consistently. And if you have any background in logic, you know that it changes nothing in terms of the underlying dynamics of the problem. I can tell you with full guarantee that both these domains are equally easy for classical planners. Okay, but obviously, if you are remembering and getting solutions from based on your memory, you will start doing badly. And not surprisingly, we found essentially that mystery blocks world, all the conventional LLMs do very badly. And this has never really changed, okay? So that's the thing that we were looking at. Apparently, we wasted too much time with the blocks world. That the other day I was looking at Google, and if I say my name, I am blocks world, apparently. But anyway, so blocks world, which is actually made fun of in AI planning because it's like its easiest problem to some extent, actually was pretty hard for LLMs because, as I'll tell you in a minute, it has action interactions, and dealing with action interactions requires actual inference and search, and that's something that LLMs are not good at doing. So they could plan. There are a whole bunch of ideas that people have about chains of thought, React, fine-tuning, etc. We have written papers on all of these, including, for example, chain of thoughtlessness in NeurIPS 2024. You have to give me credit for actually getting a paper with title Chain of Thoughtlessness through NeurIPS reviewing. So there it is. And so basically, that basically shows that in the case of chain of thought, you give an example for, let's say, last data concatenation is their problem, but we also looked at planning problems, where you give example about how to do last data concatenation, let's say 3-4 words, and then its performance improves at 3-4-5 word instances, but then starts falling down as you increase the number of words. The procedure is the same silly procedure, but it just cannot unroll the procedure far enough. If you're surprised at that, we should be, because following instructions, following advice is actually considered to be one of the original goals of AI. McCarthy basically said the goal of AI is to be able to take advice. And so in general, it's almost as hard as solving the entire AI problem. And then, so in a way, you would like to think that chain of thought allows you to give a general procedure about how to do last data concatenation or planning, and that it'll actually work with that, but that's not the way it works. Really, if you have to give examples for different lengths of problems, and that's the only way you'll get the solution accuracy. So if you think of that capitalist proverb, give a man fish and feed him for a day, and teach him how to fish and feed him for a life. For LLMs, give an LLM fish, feed it for a day, teach it how to fish 2 fish and feed it for 2 days, teach it how to fish 3 fish, feed it for 3 days, and so on and so forth. At some point of time, you will give up. Fine-tuning, unfortunately, is another thing that people have tried. It's a very, again, you can improve with both chain of thought and fine-tuning. For the small distribution of problems you're looking at, the performance improves. The question is it actually going? Is it generalizing enough? So in the case of fine-tuning, also the same exact generalization problems exist. Actually, there's this whole question about whether or not fine-tuning is really sort of, in a traditional computer science sense, is the amortization, the cost that you spend in doing fine-tuning, is it amortized over the time you're using it? So this is sort of a cartoonish way of saying that instead of just giving a planner, if you have a formal solver for a set of problems, instead of just directly giving it to that formal solver, you are basically making the formal solver or a verifier solve trillion problems and fine-tuning it, LLM on that, just to show that it can actually get it. And so there is a question as to the effectiveness of that. So in general, the bigger point I think is useful here is, in machine learning, we tend to think of in versus out of distribution, but out of distribution could be out of distribution in very far away from the distribution versus pretty close to the distribution of problems you looked at. So if you looked at 3-4 word problems for last letter concatenation and you did some more 3, 4, 5, 6 word ones, that's still out of distribution. But really what I'm saying is when you go to 10, 20 words, that's still last letter concatenation, and those actually are quite away from the ability for LLMs to actually generalize. So I think for reasoning problems, we need to start thinking about whether you can answer in the deductive closure as against just in versus outer distribution, because outer distribution, even though the name doesn't preclude you from thinking about 10, 100 word last letter concatenations, people tend to set up their experiments in such a way that it's very close to the set of the distribution of problems that the LLM has been trained on. Again, as I said, despite whatever I said for the conventional LLMs, actually people keep making lots of claims. They wrote lots of papers about this. These are well-referred papers, very well-cited papers too. And the question is, what exactly is going on? And part of it is because there are planning, as is used in common parlance, involves actually 2 different aspects. One is knowledge, knowing how to do very different things, at least how to actually achieve this goal. What are the different ways of doing it? And if I have 5 different things to do, how to make sure that the thing that I'm doing for the first one doesn't get into the way of achieving the second one, which is the interactions between the goals. The first one is about knowledge. The more knowledge you have, the more you have about how to actually achieve a very different goal in multiple different ways. The second one is in essence about search and reasoning, tends to be, at least that's the way it's been done in AI. And LLMs are great at planning knowledge, and they suck at basically the reasoning part, the search part. And so not surprisingly, if you actually looked at all these papers who said all these claims and you look at the kind of problems they looked at, they mostly looked at problems where you may have, let's say, 10 or 15 goals, but the real problem would be just figuring out one way of achieving each of these goals and concatenate them any which way, and that will be a plan. That's not normally the case for general planning problems. And so we actually, to show this, in fact, in the blocks world, we change the domain such that the actions no longer have preconditions and they don't get into each other's way because they don't delete any condition that any action can require. So you remove deletes as well as preconditions. And when you do that, suddenly the green parts keep increasing. Okay, so that's basically how you can make blocks world, which is already easy, even easier by essentially removing the interactions. And so if you want to argue that LLMs can plan, pick a domain with a high branching factor of unenumerated actions where the interactions are very, very low, almost like the MacGyver planning, where like it looks like nobody even knows how to achieve this goal, and you figure out some unenumerated way of non-standard way of doing it. But then you are assuming that if you're achieving these in non-standard ways for 3 different goals, they won't get into each other's way. So the interactions won't be a problem. So things like these 20 questions, household or web tasks over an ergodic world are examples of cases where LLMs do well. Okay, if you want to argue they can't plan, you can actually pick a simple domain with just a few enumerated actions, but the action interactions are non-trivial. That's what happens in Bloxwood. That's what happens in even more simpler domains, even in domains like Sokoban that some of you may have heard of, which is actually a classical, simple, non-ergodic domain where you can only push the boxes because of which you can get into corner cases and you can't come out. You can't get into a state and not come out. And in those kinds of cases, basically plans can be shown in post hoc that LLM plans are wrong. Okay, they're still very good at knowledge, and we actually show in Europe's paper how you can use LLMs to make the domain engineering effect easier. So you can generate the planning domain by essentially querying the LLM and do much less human intensive work. And this is essentially something that basically reduces the human effort involved in doing these domains. I won't get into this. It's an interesting slide, but I don't have time. But I want to get into the second part, which is, well, obviously these are all up to GPT-4, and then O1 happened, and then in O1, R1, all these other things, the reasoning, quote unquote, reasoning models are happening. What's actually is the difference, and do we expect all these problems to go away? So one important thing, of course, is that basically one way you can get from LLMs to kind of system 2 abilities is the two approximate ideas that people have looked at. One which makes complete sense to me, and the other one I don't yet know why it works. One is the test time scaling, especially as like an external verifier, or LLM generating multiple choice and answers and some verifier picking the majority answer, for example. Those kinds of things, you can actually explain why it works. Because you have a generator is not pass set 1 correct. You are actually improving by letting it generate multiple cases and then picking. That actually makes sense. But then that is really what normal AI used to do all the time, which is basically spend all the time in the inference time, online search. So if you remember in the Deep Blue, essentially they were doing all the search online. And when you came to, by the time you went to Go, AlphaGo, they did much less inference online, and then by AlphaGo, AlphaZero, they were doing most of it offline, and then essentially just picking the moves at that point of time. And so online search is basically was at the test time scaling. That is actually makes a lot of sense. The spectrum of test time scaling approaches, you have like the majority-based self-consistency approaches. You can have MCTS sort of beam search sort of things to look for better solutions. And then you can also, one of the things that I'll spend a little more time on is verifier. If you have verifier for a domain, you can use the generator with the verifier in a generate test loop, and you can do much better than without. And so that's what we call LLM-Modulo. There is an ICML paper. And what we are basically saying essentially is you can have a bank of verifiers, verifiers that look at different pieces of the solution. And if the LLM guesses, and if they actually don't have, if you show the problems, then that becomes the prompt, and then LLM gets another guess. The question as to whether LLM is actually following the criticism is a different issue, but this sort of a generate test framework we can show improves the accuracy, and more importantly, it's guaranteed to the extent the verifiers have properties. Of these verifiers, essentially, you can have different kinds of verifiers. You can have, for example, even for planning, you can have causal correctness verifiers, resource usage verifiers. You can have learned verifiers, which have probabilistic guarantees on the verification. And then finally, people really want to do LLMs themselves as the verifiers. LLMs are good as style verifiers. They're not as good as correctness verifiers. In fact, in iClear this month, we are actually presenting this paper showing that LLMs being used as verifiers has problems. I'll get that in a second. I generally talked about verifiers rather than solvers. If you come from a traditional AI perspective, I'm not taking the solvers, I'm taking just the verifier part. That's a useful thing because verifiers can compose. And so if you have, let's say, a planner that does work in temporal planning but doesn't know how to deal with stochasticity, you need to write another planner for that. But verifiers are, composable, and that's a very useful thing. And really, solver is verifier plus search. That's just the way most of AI works. And then the soundness part comes from the verifier's correctness, as I said. and as I said, the style versus correctness, the LLMs are not good with style, are not good with correctness checks, but they can be good with style checks. This is the Achilles paper that we, as I mentioned, this actually, we wrote this about a year and a half back, but it's showing up in Achilles now, that we basically show that if you use LLMs to check the correctness of their own solutions, the overall system's performance actually goes down, because it doesn't, one of the reasons why people think LLMs can be better at verification than at generation is computational complexity. And that's unfortunately a completely wrong argument, because as I said, LLMs actually, they're not doing reasoning, it doesn't matter what the underlying computational complexity is. And so we actually show that when LLMs do verification of their own solutions, even something as simple as CSP, SAT, and certainly also in planning, their performance actually worsens if they, versus if they just don't do verification and then just basically give the solution that comes out. Okay, but if you have a guaranteed verifier, or at least a probabilistically guaranteed verifier, then the answer is different. If you actually train the verifier itself, even if it's based on LLM discriminatively, then you can actually see more guaranteed improvements in the performance. In terms of style, this is a Comb paper, Conference on Language Models, where basically we showed that if you have a bunch of trajectories that basically are reach a same goal but have very different styles, LLMs are actually pretty good in doing kind of criticism of that style. So for example, here, if I'm asking, give me a pair of scissors, and the trajectory that the robot came up with involves giving the pair of scissors with the pointy end towards the human, typically that's a bad thing, and LLMs actually can point that out, because in terms of the trajectories they have seen, that looks like a bad thing. So this is the stuff that you actually can depend on. So the interesting question is, they will be good at correctness in only those few cases where style implies correctness. In general, style doesn't imply correctness, right? That's not a surprising thing. And then we did some of this work also for mental modeling and human mental modeling. There's an HRI paper that shows that they can be fine, but they are very brittle. If you change the prompt a little bit, then essentially they no longer are able to check whether the plan that the agent makes would be seen to be explicable by the human outside, okay? Then we also showed that LLM-Modulo improves, as I said, LLM-Modulo improves performance on multiple benchmarks and with guarantees, guarantees are modulo the verifiers. In general, I think if you look at what's happening in alpha geometry, or if you look at what's happening in programming synthesis community, they're all actually kind of can be seen as some version of LLM-Modulo, because in the case of program synthesis, you have unit tests. Unit tests are partial verification of the code you generate, and then you keep. And then Python interpreter can take the unit test and the guessed code and check if the solution that is output by this code corresponds to the solution that the unit test expects. If not, then you can actually you can ask the LLM to guess again. So this is actually a reasonable way of using the verifiers. So this is the test time scaling ideas. The question, of course, is when you're doing test time scaling this way, you're doing it fully in the online mode. In general, surprisingly enough, Marvin Minsky in his old work basically says that intelligence is integrating test part of the generate test into generate part. So if you can do this correctly, then you want to be able to somehow push it back into the generator such that its correctness improves, even if without guarantees. And to some extent, if you have LLM modulo, right, you can essentially say that after it actually generates a solution that passes the critiques, that's a correct solution that can become part of the synthetic data, then that can be used to, for example, fine tune so that the generator's correctness improves. There are obviously better approaches. That's one approach, but there are much better approaches that people have been trying on this post-training with the intermediate tokens included. So the post-training approaches rely on the synthetic data, so they're actually relying on the external verifier most of the cases, unless you can pay the humans, which is very costly most of the time. And often they're generated with classical verifiers, and the compute is basically being converted into data right now. And as I said, instead of doing fact, you're slowly generating your own reasoning web with the verifier and compute. Okay, and the LLMs are fine. And then the other thing is, So the LLMs are fine-tuned not only on the solutions, but in these cases, they're also fine-tuned on these intermediate tokens, the derivational traces that lead to the solutions. And they might come from the humans, traditional solvers, or base LLMs generating the intermediate tokens from the traces themselves, and that are being selected in the case of DeepSeek R1 with RL approaches. RL post-training can be seen as can possibly be seen as selecting among these traces. So anyway, coming to, if you look at these kinds of O1, we don't exactly know which of these pieces it does. We know what R1 does. But when O1 came about, just before that, I gave a talk at ACL on the conventional LLMs, and Noam Brown basically right after that, when O1 came out, he said, well, Rao said the blocks world can't be solved, but actually we can solve it now with O1. And so we actually went and checked that. So there's a TMLR paper that finally came out yesterday on the O1's planning abilities. Definitely, not surprisingly, actually the generator's effectiveness improves quite significantly, but of course as the length of the plan increases, they start slowly falling down in terms of accuracy. But you are actually taking higher cost. In the case of O1, we had to pay with our meager budgets, we had to pay about $8,000, $9,000 per month for a couple of months just to do this testing. That's it. Okay. So you may not be able to, achieve, you can have AGI if you have enough budget. If not, you are in trouble. Cost considerations are an important thing. In particular, if you have test time scaling techniques that are used, end users will start actually saying, I'm not going to pay this much time or this much money. And the whole deal about LLMs has been that as soon as you hit return, the answer will start come out, and that changes with the test time scaling techniques of any kind, and it will be interesting to see how the efficiency considerations come into play. DeepSeek R1, when it came out, we did these experiments on that too. It's similar, it's better than all the conventional LLMs and in the same league as O1. That's kind of nice. But more interestingly, LLM-Modulo can now become LRM-Modulo, and so you can use DeepSeek and O1 as the guesser and then have verifiers in the loop, and we can improve the performance of these guys over any given domain problems. And so that's what we show, that LLM-Modulo actually improves performance of O1 with guarantees because you have verifiers here. And then it can also sometimes be a cheaper alternative. Now I finally come in the next few minutes, I want to just get through this thoughts on LLMs that I mentioned in the earlier. Incremental compilation. Essentially, what I would like to think about is you have LLM has solution guesses, and then the verifier is checking if the solution guesses are correct. And if the verifier basically says they're correct, they become part of the synthetic data. And then that synthetic data becomes part of the next training cycle, and the LLMs parameters are being changed. And this can be done incrementally many times. And so this is what I had in mind when I was saying that essentially training the synthetic data can be seen as compiling the signal from the verifier into the base LLM. And you can do it either with SFT or RL style techniques. And so you're kind of going from pass set A to pass set 1 over a certain distribution of problems. And if you do this at test time with the verifier, we called it LLM-Modulo. Training time, essentially, it's like internal LLM-Modulo, because if you look at what, basically, as everybody said, AGI basically has become using formal verifiers to generate more data, which you are training LLM, at least right now. We haven't gone further than that. And so you can have LLM-Modulo, internal LLM-Modulo when you generated the training data to improve the parameters of LLM. And then distill time is essentially going from one epoch to another epoch, where the newer R1 model now generates the traces for the next one. This actually should not be surprising. There's this guy called Yunqian Deng and I think he's in Waterloo. His whole purpose in life, just like Karthik's purpose in life is to check every new LLM on the plan bench, this guy's purpose in life is to check to see how they're doing on multiplication problems as LLMs become better and better. And you'll notice that the green basically the green part is the correct set of multiplication answers by n problems, and you see the green frontier is slowly increasing, and that's sort of incrementally compiling more and more of the multiplication problems. And then Dimitri is actually who works with you guys. I believe this is probably the MSR work. He shows that for empty transformers also this can be done essentially. But then the point essentially what you're doing is the quote-unquote recursive self-improvement is this very costly way of compiling verifier signal into the generator, and you can look at it as a good thing, or you can look at it as an inefficient thing, and we may want to take a look at that. The last thing that I probably will have a chance to talk about is this anthropomorphization of intermediate tokens. Right now, after R1, and basically there's a whole thing about aha movements, thoughts, reasoning behaviors. The models are thinking through the problem. They're actually backtracking. They're doing self-verification, and this stuff is quite, the thing there right now. We've asked ourselves, are post-trained models really generating reasoning traces? There's really not much of a reason to believe this to some extent, as I mentioned earlier. In fact, if you look at R1's mumblings on a simple block-solved problem, it goes like this: first page, second page, third page, fourth page, fifth page, fifth page. So 5 pages of mumblings on a very small problem. And nobody has the time to actually look at these mumblings to make sense of the reasoning traces. And essentially, it's in pseudo-English, but it's not clear that is actually connected to what the solution is. The problem, of course, is how do you evaluate either one way or other? Turns out that you can evaluate formally in the sub-cases where the intermediate tokens being trained were generated by a formal solver. Some of you might be familiar with these 2 pieces of work. One is search farmer, other is stream of search, where they essentially use a formal solver to generate traces that are correct, that the formal solver use those traces on the way to the final solution. And then you actually use that as the fine-tuning, intermediate token fine-tuning for the LLM. In that particular case, so for example, search farmer basically uses A-star search. A-star search has manipulations of open and closed lists, and you have all sorts of open and closed list tokens, intermediate tokens saying the open and closed list manipulations. And this stuff makes sense again to A-star search. If you give it this, it can simulate it and see whether or not it leads to the solution. So given that, we can now do the following thing. Having trained the LLM, we can then ask it to solve new problems. When it's solving new problems, it is trained to generate the intermediate tokens because that's what it did. The point is all LLMs actually learn the style. They learn the style of the solution. They also learn the style of the intermediate tokens. So they clearly will produce something that looks kind of like this. The question is, it's very hard for humans to figure out they're right or wrong. Because we have A-star search, we give this to A-star search and ask it, okay, can you just simulate this and see if you go to the final solution? And it turns out about 40% of the cases, even when the solution is right, the traces actually are wrong. It wouldn't have led A-star search to the solution. So you did some scratch work and you gave the correct answer, and you're expecting that the scratch work might be actually correct. If this is the case, then does the correctness of the traces matter even for training? So we did this other thing where we generated the traces for problems. So you have trace 1, problem 1, trace 2, problem 2. You make the problem 2's trace, problem 2 be the solution for problem 2 be the one for the problem 1, and vice versa. So each of the solutions are preceded by probably wrong traces, at least as far as the A-star search is concerned, and we retrain it. And it actually reaches and we could do this for transformers, right? Because we can actually afford to do this even in the universities. And we see basically that it gets to the same level of accuracy, which essentially means what is helping is not the correctness of the traces, it is these intermediate tokens. So it sort of, you might say, if it helps, why do you care? Well, it engenders false, undeserved trust in the end user. So if the user can't be sure whether to trust the solution or not, and there's some pseudo-English intermediate tokens, they're more likely to believe the solution is correct. And you don't want AI systems to make a frontal assault on our cognitive flaws, so it makes no sense. And secondly, actually, if in fact the pseudo-Englishness of the traces don't matter, then it becomes an albatross on the RL phase. And so you should be able to deal with intermediate tokens which don't actually have any pseudo-English thing that may make sense to humans and just look for any arbitrary intermediate tokens, including some people have been saying continuous latent space, pick tokens from the continuous latent space, and that can actually improve the performance, and if that in the end performance, and that might be a very reasonable thing to do. All we know is the intermediate tokens help, and there exist some intermediate tokens that would help, and so this is what the learner is trying to figure out. And actually, I don't have time on this, but the last thing I want to mention is that the derivational traces, the RL part is an interesting thing. I know some of the people here also are looking at it. I think RL is a great idea, but it's not completely clear to me, at least in the R1's case, whether RL is really being used or whether you could have done incremental SFT. The difference seems to me more between like SGD and SGD and batch gradient descent. So as long as you change the LLM parameters and use, during the training and use that to, look at the newer problems. So you essentially are incrementally improving the LLM's parameters significantly, over a period of time. And that seems to be more of an important difference, and it's worth checking. If any of this makes sense to you, there's, there's a couple of ML Street Talk things where I go into more details on general connections to these ideas. And I have like a ICML tutorial that was done before LRMs, so that goes more into details about the LLMs and the planning abilities. And as I said, I had the ACL paper, and these two papers might make sense. And then that's a summary that I mentioned, that essentially the post-training and the test time scaling are the things that we are looking at. Test time scaling to me makes sense, but it actually kind of breaks the illusion of LLMs giving answers right away because you're actually doing online search. And the post-training is trying to somehow compile it back into the generator. The question is, under what conditions is post-training going to work is something that we would like to understand. And that's all I have. And thank you for your